Good afternoon. Today's lecture will be about induction motor control and protection. In this lecture, we'll cover speed control of induction motors, braking of induction motors, electrical braking, and also methods of protecting induction motors against various electrical faults. So we shall start with induction motor speed control. So when we talk of induction motor speed control, what we are looking at is we want to look at the way in which we can control the speed that we get out of the machine. When you look at the torque speed characteristic of the induction motor, we noted that the operating region, which is here, is indicated by a speed that is very near to the synchronous speed. So the difference between the synchronous speed and the actual mechanical speed is the slip of the motor. So when we are looking at the control of speed is we want to understand how we can change the speed from the naturally occurring speed that we have. So when we are looking at the speed control, we are looking at how do we change from a speed that is one value to a speed that is another value while still providing torque to the load that we are supplying. So when we have induction motors, there are two general characteristics that we look at. The first is the slip, and the second is the synchronous speed, or NS, right? By varying either of these, you are able to change the speed that the motor will be actually running at. So either of these properties can be used to vary the motor speed. And when we talk of slip, we have two possibilities in which we can look at it. We can change the line voltage, or we can change rotor resistance. This is only in wound rotor machines. It is not available in squirrel cage machines. We shall look at that shortly. And also when we are looking at the changing of the synchronous speed, you have two possible options. You could change the frequency of the machine, or you could change the number of poles. And under frequency, there are various ways of doing it, and under number of poles, you either have the method of consequent poles or the method of multiple stator windings. Right? So let's look at these in turn. So first of all, we have the variation in slip. So let's see first when we have slip as the main method of changing voltage, how do we go about it? So there are two particular ways we can do, which is changing the line voltage. Now when you apply a line voltage to induction motor, there is a change. You can change the value of that voltage according to whatever you would require. And changing of the line voltage will result in a torque slip characteristic that is shown here. So in these three different lines or graphs, you have three different voltages being applied. So the first voltage, V1, is a lower voltage than V2, and if we increase it, you can get at V3. So you have the voltages. As you increase the voltage, you have different torque speed characteristics that the motor encounters. The reason for this is the torque is directly proportional to the square of the voltage that is applied. The square of the voltage that is applied. And that's why you see a drastic change when you change the value of the voltage. Now bear in mind, even if you're changing the value of the torque, what we are really looking for is the value of the speed. We want to see how we can change the value of speed with a certain load. Now if your load line, the load that you want to supply, is given by this characteristic, by matching the various torques that you apply to the load and changing the voltage, you can be able to have, for the same load, you would be able to apply a different speed to that torque, yeah, based on the three different curves that you have. So if at V1 you want to supply the load at that level, you would get the speed at that value. If you are applying voltage 2, you would get the speed at that value, and so on and so forth. But remember that, as we said, the operating region is a certain limited portion of this, yeah? The normal operating range of our machine is usually around here. What this means is that if you're changing slip as your way of controlling speed, you have a very limited range in practical terms within which you can actually vary your speed. So the speed that you can actually have will be very limited if you are just changing slip. Okay, so that is changing the voltage that is applied to control the speed. We can see that's a very limited speed control. The second method we would use, which is, as we've said, only available for wound rotor induction motors, it is the increase or decrease of the value of the resistance in the rotor. So here we are talking about rotor resistance, yeah? The resistance within the rotor. Remember that we said that the rotor itself, in order to produce torque, there is a current that is flowing within the windings of the rotor, all right? And those windings have their own resistance. So if you were to change the value of the resistance within the rotor, you can be able to consequently have a change in the value of the torque that is coming out of that and the speed that is coming out of that. So if we apply the same principle that we had, whereby we are looking at our operating region, you can see that your actual amount of, or the values of speed that you can see are as indicated there. So the speed control that you have will be as shown in that one. Once again, this is a fairly restrictive range of speed that you can control simply by changing the rotor resistance. So it's not quite, it is not a drastic change of speed. You're only changing the speed to match the torque that you would want to supply. So if you want 400 Newton meters, the same amount of torque at different speeds, you would be able then to change the rotor resistance and you get the same torque, but you have different speeds of motors. This is applicable where you have various loads and applications that require a constant torque, but maybe a varying speed. So here you have constant torque for variable speed, and that is your application. So apart from changing the value of slip, we've said that you can also change the value of the synchronous speed. So the motor control with the value of slip is limited. Okay, but if you want truly a wide range of speeds, then you would have to change the intrinsic value of the synchronous speed. Now remember what constitutes or what determines the synchronous speed. Synchronous speed is given by 120 F over P, where F is the frequency and P is the number of poles within the machine, all right? And poles depends on the configuration of the windings, the stator windings. Okay. And the frequency of the speed is a characteristic of the supply voltage, right? Or the supply, power supply, let's call it that way. Okay. Now, since we know these two, and since we are able to vary the speed purely using these two elements, you can be able to now have different means by which we can change the speed. So let's start by looking at the number of poles. If you're looking at the number of poles that you would want to have in the machine, ordinarily you would not be able to change that, because as the machine is running, the number of poles that you have, if we can look at our motor again, remember that the number of poles is determined by the stator windings over there. Okay, and obviously as the machine is running, you would not be able to change on the fly, as it were, the configuration of the winding. These windings are fixed during the construction of the machine. So how do you change the number of poles? You change the number of poles by introducing switches that would change the configuration of those poles. Electrically, you can change the value, or you can change the number of poles. And that is where we now talk of the consequent poles and the multiple stator windings. So let's start with the consequent poles method. So by looking at the method of consequent poles, let's take one of the three sets of windings. So one set of windings in the stator, of stator windings, right? If one of them would look like that, for example, say you have out of your phase, one phase of the stator windings, you have a number of windings that look like that. The coils are configured in that way, such that they are on one side of the stator against the opposite side of the stator. Okay, and you have the windings such that if you have the current flowing in this direction at this instant, IT, the windings then the windings then would have current flowing in the direction that is shown. Okay, now using our principle of the magnetic field that is induced around a current carrying conductor, let's say that the current flowing in the downward direction is indicated by current flowing out of the page or the screen, and flowing upwards is indicated as current flowing into the screen. So if we have them in that way, we would see that our A1 arm of the winding, that is this section, which is represented here, would therefore be current flowing inwards. And if it is flowing inwards, or rather outwards, sorry, and if it is flowing outwards, it is a counterclockwise direction. So the direction would be counterclockwise. For A1 prime, which is here, you would have it flowing into, so that is a clockwise direction of the current. For A2, which is here, flowing upwards, it is also an inward direction, so it is a clockwise magnetic field. And finally A2, which is flowing downwards, you would then have a current that is flowing out, and you would have a counterclockwise direction. So you can see in this particular instance, you would have the general resultant magnetic field in this area moving downwards, which we can configure as our south pole. And here it is also moving downwards, so it is considered to be a north pole on that side. So you have your general magnetic field moving from north to south. In between, you have from the lower part magnetic field in that direction and the upper part in that opposite direction. So here they would cancel out. Here they would also cancel out because you have a magnetic field in the opposite direction. Okay, so here you have a resultant magnetic field that would be in the direction that is shown. So you have, based on your diagram that we are showing here with one set of stator windings, you then have a magnetic field that is in such a configuration that you have two poles, a north and a south. Okay. However, if we were to change this configuration, remember we are showing our windings that are here. The windings up to this point are inside the stator. These are fixed inside the stator. What we have outside here, if we were to connect them through terminals, the way in which you connect these terminals, so this is A1, A1 prime, and A2, A2 prime. The way in which you connect these terminals determines how the magnetic field, how the current will flow in the stator, and how the resultant magnetic field will be generated. So if we had a way of changing around the connections such that the directions of current flow are slightly different from this, you would then be able to have a different configuration of the magnetic field, which is what we can now do here. So if you see here, current flowing on the A1 side is downward and upward, and the A2 side upward and then downward. But if they were all in the same direction, so down, up, and down, up, all right, the same kind of configuration. If we use this now configuration, we would then end up having the magnetic fields that are here slightly different from what we had before. So if we take our A1 magnetic field, which is here, would then be counterclockwise. Our A1 prime would be clockwise. A2, which is over here, now because we have a different configuration from the one above, here we had it moving upwards, whereas on this side it is moving downwards. So you have an opposite. Whereas we had clockwise here, you will then have counterclockwise in this new configuration. And finally, A2 prime, which is also opposite to what we had before, will then now have a counterclockwise, or rather a clockwise direction. So that looks like that. Okay. So what then happens is you will then have your north pole here and your north pole here. And then what you notice is you have also similarly some resultant magnetic fields that are going in these directions. So you have, if I can draw these out, the continuing magnetic fields from above and the ones from below are all going in that direction. The one from above and the one from below all going in the same direction, so that you have south pole, and north pole, north pole. All right. What you end up having, these south poles that you have now created here in between, which were not here before because these were being cancelled out, you now have what you are terming as consequent poles. So these are poles that are consequent, and they result from the different configuration that we have from your winding. So the terminals are connected differently, and they therefore result in 4 magnetic poles instead of just 2 magnetic poles. So you have a north-south configuration. Okay, so simply by changing, and if you notice what has happened here, A1 is connected to A2, whereas in the other one, A1 is connected to A2 prime, right? So there is a reversal of one of the directions of one of the parts of the winding itself. and that results in your consequent poles. So that means that you have then increased the number of poles by a ratio of 2 to 1. You have twice as many poles by changing the polarity, as it were, of the windings themselves. And if you go back to now our formula, so this means that if you had NS1 with 2 poles, NS2 with 4 poles will then have half as much speed. So whereas if your NS in this case was say 1500, your NS2 with 4 poles will be 750 RPM. Okay. So that is the method of consequent poles. And the other method that you can then use is multiple stator windings within the same stator. So this means that you switch between 2 different windings. So imagine if this is your induction motor, you would then have within these windings, you have 2 different sets. So one set of windings might have say 4 poles, another set of windings might have say 6 poles. So you have 2 different configurations mounted within the same stator. And only one set of windings operates at a specific time. So you are either using your, for example, 4-pole winding or your 6-pole winding. Yeah, and each set has a different number of windings in itself to get a different number of poles. However, this method, of course, obviously is very expensive because you would then have essentially double the number of windings than what you're actually using. And at any given time, you're only using one out of the set of windings that you would require. So it's like having 2 motors in one, whereas you only have the output of 1 motor. And finally, therefore, we've looked at the slip. We've looked at the way you can change in line voltage and rotor resistance. We've looked at synchronous speed, the number of poles. So finally, let's look at what happens when you change the frequency of the machines. So in the case of changing the frequency itself, right? Previously, we have only been changing the number of poles. If you would need to change the frequency of the machine, you would then have, if we change the frequency here, you can be able to change in a linear way the number of or the speed at which the motor is running through changing of the synchronous speed. So how do you change the frequency of a motor? You change it through what are called variable frequency drives. So variable frequency drives use a method of switched power supply in which it is either off or on. And by changing the magnitude of the power supplies, you then have a different values of voltages that in the end appear to the motor as if they are an AC voltage. So those changing frequencies, those changing power supplies, which we call pulse width modulation, you change the value of the length of the pulses that you have into that you're supplying into the machine, and that gives you a pulse width modulated wave that appears to the machine as an AC wave. And that through that method you then have the variable frequency, and by changing the length of the pulses that you apply, you can then change the wavelength of the frequency that you're applying, which you can see here. If you have longer length pulses, you can then have a longer wavelength as you have there. Shorter pulses, you can have a shorter wavelength or a shorter, a higher frequency, right? And therefore, by this method, you are able to change the speed of the induction motor. So those are the main ways in which we have varying induction motor speed, or we can control the speed of induction motors. We talk about protection. Now, when we look at protection of motors, you know, you are going into industry. Most of you, I hope, will go into industry, and we need to look at whenever you have any useful machine or electric device that is consuming energy in order to serve a useful purpose, either whether it is converting energy like the motor, which is converting from electrical to mechanical power, whether it is lighting, where you convert from electrical to light, heating, where it is electrical to heat. Any circuit that you have needs to have protection. These are the main types of motor faults that we have, right? It's a comprehensive list of all of them. And when we are looking at these various faults, we look at what is the implication, what is the cause of the fault, what is its effect, and how does it affect the motor, right? The consequences of the motor failing are the ones we talked about previously, but this is now the technical aspects of what can happen to a motor. So there are various kinds of fault. I think these are 8 of them. You can have a short circuit, which is you have a short circuit from either phase to phase, so say red to blue, or you can have phase to ground, whereby one of the phases gets, you know, somehow gets a connection between it and the ground. It shorts to ground, or you can have winding to winding. Winding to winding means within the motor itself, you have the insulation that is inside failing, and you have 2 windings which have possibly been carrying different, which are carrying different phases. You have them kind of shorting out and being connected to each other, right? This can be due to a current surge. Current surge would be either you have, you know, an unexpected load or various other elements that are there. And you have stress in conductors. So stress in conductors means the amount of current that is being carried within the individual conductors, the wires inside the windings, becomes so much that you have I squared R heating aspects that literally burn out the windings. So you tend to have now burnt windings as an effect of that. When you have your voltage being applied, if the motor is expecting 415 and you have, say, lightning or an electrostatic discharge or a sudden disconnection of the load, you have excess voltage, which is more than what the motor has been designed and rated for. The primary effect of that is you suddenly have the insulation breaking down. Insulation of all conductors is rated to a certain voltage, above which it breaks down. Yeah, the dielectric properties of the insulation material are such that if you exceed the voltage that is rated, the material will no longer insulate between. And of course, you know, most of us have seen what motors look like. You have very many thin conductors with micrometer thick insulation. So if the voltage breaks that down, you then have a short circuit, which leads to the same impact of burnt windings. So these two, the short circuit and the voltage surge, cause direct burning of windings because of the electrical effects of the motor. Now the others, the rest of the effects that we look at, cause overheating of motor. These are kind of indirect effects of the various problems that we are talking about. The first 2 faults are direct electrical because of the situation of the circuit. Either the current is too high or the voltage is too high, and that is what causes those. These other ones below are due to the circumstances in which the motor is operating. So let's look at them in turn. So you have an unbalanced voltage. An unbalanced voltage means you have a 3-phase induction motor. It is supposed to receive 3 phases, each with 240 phase voltage or 415 line voltage. And for whatever reason, you are not able to supply that. So what might happen is, if you have 3 phases, it can be even something as Kenya Power, the supply that is outside there, your 3-phase supply, one of the conductors breaks, one of the wires that are outside your own premises breaks and Kenya Power's supply is only supplying, say, red phase and yellow phase, or yellow phase and blue phase, whatever it is. This is a situation we call single phasing. Yeah. Even though it is you are supplying two phases, generally we refer to it as single phasing. It is one of the most common problems or faults that occurs within motors. I would say from my experience, maybe like 50%, actually I think more than that, maybe like 70% of all burnt out motors or motor faults are caused by single phasing. And that is, it's not just at the power supply side, you can even have it occurring even within the terminals of the motor itself. If one of the supply cables of the motor directly supplying to the motor has a problem, you know, it breaks or whatever reason, you will only supply two phases. So what happens in such a case is you have two phases being supplied and one of the phases being not supplied. And you will remember from your AC circuit theory, what are the effects of that? You have almost 1.5 times current flowing through the two phases and zero flowing through the one that is disconnected. What does that mean? You have reduced torque available and you have increased losses, but more importantly, you have your motor having a high current being flowing through the two phases, trying to reach the torque that is being demanded of the motor. And in most cases, if you don't switch off the motor in time, you will have a total failure of the windings whereby they will burn out and the motor will stop running and disconnect. Right? Voltage dip is the next one. If you have lower voltage, that means the amount of power you are supplying into the motor is less than what is expected for the load that you are running. What might happen in that case is you have reduced torque available and increased losses, and therefore your load will exceed what the motor can supply. The demand on the motor is more than what it is able to supply using the voltage that is being supplied to it. This can be caused by an instability in main supply. We've heard of brownouts, or you can have loads that are too high for the rating of the motor. If it's a 7 horsepower motor and you're connecting a 10 horsepower load, these are the kind of things that can occur, right? Another different problem that can occur is harmonics in the supply. Usually when you have a supply of voltage, you would usually expect that it would be a sine wave, right? If you have harmonics, the sine wave is not very clean. You would tend to have various artifacts within the voltage itself, and this roughness or these spikes, sometimes they are spikes, sometimes the wave is not exactly sinusoidal, it might be a square wave. Those have an impact on the way the magnetic fields are formed within the motor. So you have your rotating magnetic field being formed erratically. So it's almost like the magnetic field is not rotating at a constant speed. Yeah, these are non-linear loads, or rather these are caused by non-linear loads connected to the same supply. Next, we have a long starting period. This simply means that you take a while in bringing the motor up to its correct speed. Related to this is also running the motor at a lower speed by electronic means or whatever other frequency changing means for a long time, which it is not rated for. This can be caused by a voltage dip or a high load, or even the method itself, the method of starting. We will talk about starting a bit later on. This also causes overheating. Next, we have locked rotor and overload. So those two are cases whereby you have a mechanical load that is too high for the rating of the motor, right? You have high loads that prevent the motor or demand more torque out of the motor than it is able to supply. So you would then have either a mechanical problem if the shaft is connected or coupled to a load that is fixed, or a bearing has collapsed even within the motor. If one of the bearings collapses and the rotor is not free to rotate, you will then have an overcurrent as the motor tries to generate or create enough torque for it to overcome the locking of the rotor. And if this goes on long enough, you have overheating, and it can be a complete failure of the windings of the motor. Excuse me. Similarly, connection of high loads, as we have said, for a long period of time, you will have overcurrent, and if the overcurrent runs for too long, you would then have a situation whereby your motor or the windings of the motor would fail because the ratings have been exceeded. Okay, so those are the types of faults, or the causes of the faults that we have. So how do we prevent them? We've talked of two types. We had short circuits and which cause burnt windings, and we had the overloads, which manifest themselves as high currents. So let's look at those two in turn. So looking at short circuits within the motor. So as we said, this is a brief surge of current which occurs, right, for various reasons, either due to the short circuit or due to a voltage surge. It is caused by either damaged insulation, as we had said, loose connectors. We mentioned foreign objects in the motor. This is one we didn't mention, which is a piece of metal that would short circuit exposed uninsulated components of the wire. Ingress of water. Water, is a conductor, and it is a very dangerous element. That's why we have motors having IP ratings, so that if they're operated in areas where there's a risk of water, it can prevent the water from coming in, or you can even just have an error in wiring. So those are related to what are those, what we had listed before. The results of the same are melting of the conductor contacts. We talked of arcing, fire, and insulation damage. So how do we protect them? It is as simple as fuses. Fuses are designed to disconnect the circuit or open the circuit when the current is too high. So in these cases of short circuits, the current is in these kinds of cases, we have currents that are beyond what is safe for the motor. So we want to quickly disconnect the circuit so that we can address the issue that is there. The fuse opens the circuit without the need for human intervention, and it allows us to take care of whatever emergency is there and remove the source of the short circuit, whether it is a poor connection, whether it is the water, the foreign objects, etc. Fuses are kind of permanent. Once a fuse blows, you have to replace it. The alternative to that, of course, is the electromagnetic circuit breakers, or CBs, or MCCBs, which are means by which you trip the circuit. You disconnect the circuit when the circuit breaker device senses that you have too much current flowing. It can sense over voltage or over current or various other elements of the circuit that are undesirable, and you can set them to a range. You can set it so that it allows a small amount of overcurrent for a short period of time, or you can have it set so that if the overcurrent is very high, even with a short period of time, it will still disconnect the circuit. Okay, so those are the two main methods of protection against short circuit. Secondly, for overload current, these are kind of indirect. The previous one we talked of, they were direct causes of faults within the motor. These are indirect causes, such as the mechanical problems we had. We talked of the locked rotor, the harmonics, the voltage dip. In themselves, they do not cause a problem in the motor, but over time, because of an increased current, they lead to an increased temperature. And it is this temperature, the overheating that we had talked about, all these we talked of, overheating within the motor, that is the dangerous element that we want to prevent. The risks of that, as we had said, even if it doesn't have an immediate effect, you can decrease the motor lifespan. With time, you might find that you begin to see a blackening of the insulation. The insulation weakens, and you start having minor shorts within the winding, and the motor does not operate as it is expected to. Or you can start having interruptions of operation, whereby the motor overheats and it is unable to rotate as it is supposed to. The main method of prevention of or protection against overload currents is the overload relays. These are devices that sense, usually by means of sensing too high of a temperature, they provide a signal or they disconnect the circuit directly by sensing that the temperature is too high, and they open the circuit. We use relays because they may not be directly connected within the circuit. So it is kind of a second device. Yeah, it is a sensor that provides a signal to a switch that will disconnect the circuit. Okay, we will see a bit about those when we are doing starting of three-phase induction motors. So the types of relays, you have a normal bimetal strip overload relay. This is very similar to what is usually used within ions, electric ions. You have electronic overload relays, which have a bit of power electronics and circuitry there. And you have thermistor probe relays, which are also electronic devices that now feed the signal into a control circuit. Yeah, so this is a double indirect method. You have a control circuit that is controlling the motor, usually within the confines of a variable frequency drive or some other kind of speed control device that you would make use of to control the operation of the motor, right? So that is a brief overview of the protection of three-phase induction motors. Please look into the texts. These are, as I said, they are not very technical aspects. It is just you need the awareness of what are the main causes of faults. Now let's take a look at electrical braking of induction motors. So what you're seeing on screen is the torque speed characteristic of the full range of induction motors as we had seen previously, right? So starting from negative speed, where we had indicated a braking region, then you have the quadrant which has the motor region, which is the normal region of operation, whereby you have a positive torque and a positive speed. So what happens if you are either in this region or in the region where you are with negative torque or with negative speed? This is negative torque, right? And that is what we make use of when we are talking about electrical braking. These are two of the methods that we use when we deal with electrical braking. Instead of, if you want to slow down the machine, right? Say your machine is operating at that point. If you want to slow it down to zero, to a speed of zero, how do you get it to reduce its speed in a safe manner? Okay. Generally, you would use mechanical braking, which is the use of friction, brake pads, slowing down the machine, and you stop applying a voltage at a certain speed, at a certain level, and then you slow it down to a range which is what you need. If you want to get it down to zero, you can use any of the options that you're talking about as an alternative to mechanical braking. Now, there are four main ways in which we carry out electrical braking, which, as we have said, these are non-mechanical means of braking. All right. So first off is countercurrent braking. Now, in countercurrent braking, we are changing the direction of the motor, and that is here. All right. We take this region, counter current braking, right? Whereby we are trying to change the value of the speed so that it is negative. And we do that by reversing the direction of the two of the phases. So actually, the applied input power is seen as moving in the opposite direction. So what happens is the field in the stator, the rotating magnetic field, changes direction. And consequently, the torque that is there, or rather the speed of the rotating magnetic field, changes from being a positive ns to being a negative ns, which is what we have just talked about. And by that way, you will reduce your speed because the value of slip is much, much higher. So if you have, you see your slip is ns minus n over ns. But if ns is already negative, yeah, it is a value that is much greater than what you would have, and therefore the relative difference between the speed of the rotating magnetic field and the mechanical speed itself is very, very great. Okay, so that is countercurrent braking. Let's look at over-synchronous braking down here, first of all, before we look at the other two. Over-synchronous braking is driving the motor in this region, in the generator region. So essentially what we are doing here is, whereas the normal operating region would have a positive speed that is near to the synchronous speed of the machine itself, in the over synchronous mode, you would then have the motor being operated as if it is a generator. That is, the speed that is there is greater than the speed of the rotating magnetic field. It is greater than synchronous speed. How we can look at this practically and in the real world, physically, is that the load essentially drives the motor. Instead of the motor driving the load is driving the motor. Almost as if you had, it can be analogous to if you have a lorry that is going downhill, that lorry will eventually reach a point, if it is left to freewheel, the load itself, the gravitational pull of the load, will drive it such that gravity is almost inputting power into the engine itself instead of the engine driving the load. And it's a similar case with over-synchronous braking. By that way, because you're having the load applying the power, you then don't need to have your machine being driven by the voltage that is there, and therefore eventually the energy itself will, the load's energy will dissipate and will change into, or rather will reduce it to a zero. So it is almost as if you are changing the speed going down to zero from a negative value until it reaches that zero that we're talking about. So that is over synchronous braking, whereby the load drives the motor. Two other methods of electrical braking instead of using mechanical braking. One of them is the injection of DC current. So normally you would have in the motor region, you'd have your rotating magnetic field running at synchronous speed and your rotor running at a mechanical speed with a value of S as the slip. In the case of a DC injection of current, what then happens is, instead of having NS, you then have a speed of zero. The speed itself is zero. The rotating magnetic field, rotates at 0 RPM, right? And this means that the value, the difference between the relative motion of the rotor itself and the rotating magnetic field is so great that it tends to reduce to zero. Remember that during the operation of a synchronous, or rather an induction machine, the machine, the rotor is always trying to catch up to, in quotes, to catch up to the speed of the rotating magnetic field. But if the rotating magnetic field is 0, that means that your rotor will be having such a great difference in speed that it will try to reduce itself also down to 0, thereby braking. Practically, that is down to braking. But you need to note that it needs to be at a low voltage as the only resistance that is there, because you're not converting any of the power into rotational power. It is all being dissipated by the resistance of the rotor itself. So that has to be run at a low voltage. You will also, in addition to putting in a DC current, that DC current will have to be at a low voltage. And finally, you have electronic braking. And electronic braking simply means you change the frequency of the magnetic field. So if you have Ns is equal to 120 F over P, if this F tends to 0, that means that your Ns will also tend to 0. And likewise, your rotating magnetic field will go down to 0, and your rotor will also follow it down to 0. So you are electronically reducing the frequency of your power supply down to 0. And so those are the main ways in which you can brake your machine, bring the speed down to 0 through non-mechanical means.